So continuing with MAT 221, this is section 1.1. We talked about monotonic functions, or functions that only increase or only decrease. Their rate of change is always positive or always negative. For instance, in this case, the rate of change is always positive. Here, the rate of change is always negative. All right, for section 1.2, this is on modelings and change. Again, that was a really quick review of pre-calculus topics. Mathematical modeling is, or a mathematical model is a mathematical description, which often means of a function or an equation of a real-world phenomena, such as size of population, the demand for a product, the speed of a falling object, concentration of a product in a chemical reaction, the life expectancy of a person at birth, the cost of emissions and reductions, and so on and so on. There are so many applications that we'll use in calculus and in mathematics. The purpose of a model is to understand the phenomenon and to perhaps make predictions about the future, which is an extrapolation, as we know. So what we often do here is we take a real-world problem, we try to make a mathematical model, we use to solve this to make mathematical conclusions, but then we interpret using real-world predictions and bringing in real-world concepts here. Sometimes the math might be correct, but the real-world application might not, and it all depends on the context. So a mathematical model is never a completely accurate representation of a physical situation. It is what's called the idealization. It's what we ideally would like it to be. A good model simplifies reality enough to permit the mathematical reality and calculations to be accurate, to provide us to make conclusions. So some common functions that we use for modeling from pre-calculus. This is your library of functions. Linear models. So let's go quickly through linears. Polynomials, power functions, rational functions, algebraic functions, trig functions, exponential functions, logarithmic functions. Do you remember all of these functions? These are all functions that we studied in pre-calculus. We need to go through them really quickly, and then we're going to utilize many of them as we go through our calculus course. First of all, linear models. We studied three forms of linear models. One was called slope-intercept form, the most common of all forms of our linear equations. It is y equals mx plus b. Nice, but not really the one we'd like to use in calculus and collegiate math. This one, however, you might not have seen, or a form of this, insert x minus x1 plus I actually changed this and stopped my video for a second to edit my PowerPoint here. Pointslope form. This form of the equation is the one that we will actually be using most in mathematics, in upper level mathematics and calculus especially. This says y equals m times x minus x1 plus y1. In this particular form of an equation, we need the slope and some point on the curve, or 2 points on the curve where we can find the slope, and a point on the curve. This first one, we only need the slope and the y-intercept. And then the third form of an equation of a line, which a lot of students think we actually do use this every once in a while, but number 2 is what we use mostly in calculus, and that is ax plus by equals c. Remember, lines with equal slopes are parallel to each other. Lines with negative reciprocal slopes are perpendicular to each other. This is all stuff we learned way before calculus. Here's an example of a linear function. It says if a linear functions are most common functions, a function is linear if its slope or rate of change, remember, is constant. So here's an example. Given the following data of the chirp rate of crickets at different temperatures. So we have at 40 degrees, 55, 72, and 94, and we have these are the number of chirps per minute. First question, what do we notice about the slope? So let's look at the slope of these functions. If I took the slope, which is change in the the output value over the change in the input values, what do we notice about that? Well, we notice about the slope? We could calculate the slope of each of these points, where each of these actually are data points, right? We could say this is our x input, this is our y output, x input, y output, and so forth. So let's calculate the slope. We could say an output of 60 minus an output of 0. Remember, it's change in y over change in x, or change in output over change in input, which is 55 minus 40. That ends up being 4. Now, if I do the next 2 points, if I said 128 minus 60 over 72 minus 55, I get 68 over 17, which also equals 4. Or if I did 216 minus 128, 94 minus 72, I still get 4. What do I know? I notice I have a constant rate of change. So I notice that the slope is remaining constant. This is an indication of a linear function. So what can we say about this function? This function must be a linear function because it has a constant rate of change. The slope remains constant. So what does that tell us about the crickets? So let's talk about in context. What does that tell? What do we know now about the crickets? We know now that as the temperature is increasing, the number of chirps per minute is increasing at a constant rate. We have a constant linear rate of change. What's the significance of the 40 degrees Fahrenheit? Well, what we notice is that the crickets don't even seem to chirp until it is at least 40 degrees Fahrenheit. Notice there's no chirps until we reach at least 40, and then we start chirping. Can we write an analytical expression or a formula for this function? Yes, I'm going to write it a linear expression in point-slope form. So you notice point-slope form is, I know my slope is 4. I'm using my variables as c for my chirps, f for my input in degrees Fahrenheit. So c of f equals my slope of 4. My input variable is f, so I replace that x with f, minus the first x value, or nx value, so I put that x value there, x1, plus y1. So this is y equals mx minus x1 plus y1. Now, if I distribute this out, I would get this number, which is 4f minus 160. There's the linear equation for this data. All right, next, a quick review of polynomials. Now, this looks daunting, but remember, polynomials are really pretty simple. The function p of x is called a polynomial if it has this type of a look to it, where these are just subscripts. This is a coefficient times x to the n plus the next coefficient times x to the n minus 1, and so forth, where n is the non-negative integer and the numbers a sub 1, a sub 0, a sub 1, a sub 2, and so forth are the coefficients of the polynomial. The domain of a polynomial in the real number system is always from negative infinity to infinity, and the leading coefficient cannot equal 0. Otherwise, n is considered what's called the degree of the polynomial. For instance, here is a function. This is a polynomial of degree 6. It has 1, 2, 3, 4 terms. 2 is a coefficient. X to the 6th is its highest exponent. Therefore, it is its degree. And then we have negative 1 times x to the 4th. Then we have plus 2/5, which is the coefficient, to x to the 3rd. And then plus radical 2, which is just a number, which is a constant term. This is a polynomial of degree 6. A polynomial of degree 1 is of the form y equals mx plus b, actually, so it is a linear function. Polynomials of degree 2 look like this. This is ax squared plus bx plus c. These are called quadratic functions. We know that the graph of a quadratic function is a parabola, and it's just simply we can simply shift the parabola by using transformations, but the general parabola of a equals ax squared is the general parabola that we can shift. We know that the parabola will open upward when the leading coefficient is positive. We know that the parabola will open downward when the leading coefficient is negative. These are two graphs of parabolic functions. Polynomials of degree 3 are called cubic functions. They look something like this: ax cubed plus bx squared plus cx plus d, where a, again, cannot be 0, otherwise it would be a quadratic and not a cubic. Cubics have a general kind of like an S-shaped. Figure 8 shows right here, shows a cubic function in part A, and then a polynomial of degree 4 and a polynomial of degree 5 here in B and C. This is called a cubic, this is called a quartic, this is called a quintic. Remember, we did all of this in pre-calculus. Remember, the amount of times that the polynomial turns, right, is usually 1 less than the degree of the polynomial. Then we learned in pre-calc, we learned power functions. Power functions have the form a x to the n, where a is simply any given number, and n is a different value, and we'll go through the different power functions. These are the 6 power functions that we learned. The first one is even powers. When p is an even number, here, if I said here n is an even number, all of these would look kind of like a parabolic shape, like x squared, x to the 4th, x to the 6th, x to the 8th. They all will have that U shape. The next is negative odd powers. So if I had a negative odd powers of p similar to x to the negative 1, that actually would look like this function right here. These are all polynomials of degree negative odd powers. If I have negative even powers, they are all similar to x to the negative 2, which is this function. This function almost looks like a curtain function. This is x to the negative 2, or 1 over x squared, and this one would be the same as 1 over x, which is a hyperbolic function. Which of these functions have symmetry? Well, let's look. These functions have symmetry over the, these are even powers. They have a symmetry over the y-axis. This function is a cubic function, actually, and it has symmetry over the origin. This one has symmetry also over the origin. This one would have symmetry over the y-axis. This function, which is a root function, does not have any symmetry. And this function, which is a fractional odd power, has symmetry over the origin. So we could describe that you should be able to describe the nature of each of these graphs. In other words, where is the graph increasing? Where is the graph decreasing? What is the concavity of this graph? What is the end behavior of this graph? What are the intercepts of these graphs? Are there any asymptotes? These are all things that you should be able to recall from pre-calculus. Rational functions was one of the last functions that you studied in pre-calculus. I'm sorry. They are any function that is the ratio of 2 polynomials. The domain consists of all values in which the function is defined, in other words, where the denominator is not equal to 0. This is an example of a rational function. Here, if you look, the denominator of this function would not be defined at 2 or negative 2, so it would be out of the domain, which would then also cause vertical asymptotes at those values. Everywhere else, the function would be defined, and remember, these rational functions have different shapes depending on where those asymptotes occur and if they occur. Algebraic functions are functions. We don't study too many of these in calculus, but you did look at them in pre-calculus. They're any functions that is the addition, subtraction, multiplication, division, or taking roots with polynomials. And any combination of those are called algebraic functions. And there are some examples of them. These are the graphs of those functions. I do not expect you to know these graphs. These will all be something we'll be doing in Mathematica and or on your calculator. Trigonometric functions, we use trig a lot, especially in application in biology, chemistry, and physics, and